Okay, welcome, Fanri, Lexi, Sarah, and Susanna, and Rigney. Let me share my screen and talk about what we're doing today. Okay, today is a really different day than usual. Do you know what we're not doing today?
No quiz?
No quiz. So today's the only day. Actually, I wouldn't say the only day because we didn't have the quiz the first day of class either. But basically, other than the first day of class, and I'm not sure, I'm trying to think about after there's a couple other interesting days too coming up. But so far, today is the only day except for the first day of class where there is no quiz. And there's no quiz for a good reason. And that is that if you remember, last time you took an exam, and before the exam, it was just review for the exam. So there's no new material to quiz you on. So I want to let you know I'm not getting rid of the quizzes. So Wednesday, you will have quizzes. So you definitely will have a quiz on Wednesday and Friday and next Monday, et cetera, et cetera. But today there's no quiz because there's no material to cover in terms of, talking about what happened last time. So again, there's no quiz for that reason. And I know some of you might be sad because I think that was the number one thing that you guys said that you liked on the extra credit was quizzes, but there's nothing to quiz you on today. Hopefully you understand and don't be mad at me. But let me tell you the plan today. So the plan is I will start with Q&A and then I'll recap a little bit on the exam. I'm not going to go through the entire exam because that would take, too long and we have a lot to do today. Then I want to talk about the application presentations that are coming up in not too much longer. So I'll talk about what you should prepare for. It's time to start thinking about them. And then we're going to move to, I like to call it part 2 of this class. So we have spent a lot of time in this class talking about functions of multiple variables. We've talked about vectors. We've talked about different coordinate systems. We've talked about limits and continuity and derivatives and gradients. And I want to let you know that will not come up again, unfortunately, until the final. Okay, and maybe the final review. So don't forget it because it will be on the final. But this class really is a 2-part class, and we're in part 2. So we're going to start out with the very basics. And in fact, a lot of what we're doing today, you do in pre-calc. So I'm going to give you the definition of a sequence, which you've all seen before in pre-calculus, but now we'll review it. We'll talk about the difference between explicit and recursive sequences. So it's kind of 2 different ways of writing down or giving the instructions on a sequence. Both important and both are used. Then we'll get into how do you tell if a sequence converges and what does it mean for a sequence to converge. Okay, and then we'll talk about if you have a sequence that you can recognize as a function of R1, then how does that compare with convergence? Then we'll talk about kind of limit laws. So that's things like if you add 2 sequences, or if you subtract or multiply or divide, or take a function of a sequence, what goes on. And the good news about these rules, they're what you expect. There's nothing that interesting in that. Then we'll talk about the squeeze theorem, which you had, but you had it in 2nd quarter calculus for a moment. And again, it was a brief moment. You probably didn't even have any exercises on it. It's just gone over for a short time. And now we'll talk about it with sequences. Then we'll talk about what does it mean for a sequence to be bounded, and we'll talk about convergence with bounded sequences. Then we'll talk about monotonic sequences. So then we're going to move on to the next section. We actually have 2 sections today. I put 2 sections in today because we don't have a quiz. So given the fact that I had, because of the number of sections, I had to choose between doing a section last Wednesday or doing a review for the exam last Wednesday and doubling up today. I decided to do the double up today because that way we don't have a quiz today. We can just start from scratch, but we do have a lot to talk about. And we're going to talk about series, and in particular, infinite series. So that you get last quarter when you talked about integration. Do you remember how an integral was defined? And you remember? This happened in January for you. Not with me, it was with Bruce. And you remember? Nobody remembers? Yeah, it was a limit of the sum of something, exactly. And in particular, the limit of the sum of something is what an infinite series is. So we're going to be looking at infinite series. We're going to do more general ones with integration. You always have the something was a very specific something. It was like an f of x plus h. It was a f of a plus b delta n. Do you remember that stuff? I'm not going to get involved in that, but we'll talk about in general infinite series. Then we'll talk about a very special example of a series called harmonic series. So we'll look at the harmonic series, and that's a very special series. We're going to be using it a lot in the next bunch of weeks. Then we'll talk about algebraic properties of series. Also easy. Okay, they're what you expect. Add 2 things, well, you add the series. There's nothing really special. So we'll talk about that. Then we'll get into another very important classification of series. This you actually get in pre-calculus, and those are geometric series. So that's more of a review, except I'm going to be kind of catering it towards what we're going to be doing soon. And we'll have a theorem about geometric series and convergence and a formula for it. Then we'll talk about telescoping series. That's also a very special kind of series. And in particular, these last 2 types of series are series you can get a formula for. So you can actually add them all up and know what the answer is. And I will let you know that is very rare with series. So there are basically 3 types of series. You can add them up and know what the answer is exactly. One is geometric. The other is telescoping. And the third is power series, which is not today. We're going to spend a whole week on that. And that's actually the most important one. And that comes later. So that is the plan of the day. I can ask you if you have any questions. Normally I say any questions on the homework problems. But do you know what the homework is due today? The answer is there is no homework due today. So you probably don't have any questions about homework. But if you have questions about other things, and I'm going to do an exam recap. So probably not about the exam itself, because that I'm going to talk about. But anything else? My guess is no, but you might. Any questions? Okay, I want to just briefly, I'm not going to go over every problem on the exam. That would take, over an hour. But I do want to mention some things about the exam. The first thing, and it's going to be hard to get used to because you've been a community college student for a long time. But one of my goals at this point is to get you ready for the university, to give you a sense of reality. Now, I'm not going to do everything about getting you ready. One thing is that I'm not going to have 200 students in the class, which is what you would have, by the way, if you went to, say, UC Davis. There'd be 200 students in this class. It'd be totally different. Life is different. So just let you know, when you get to the university, not all universities, but many universities, calculus is gigantic. Literally 100 students would be tiny. Okay. Yeah, Cal Poly's smaller. But where I went UC San Diego, also where I taught at UCLA, giant classes. The Cal States tend to be a little smaller, but a lot of them are big with the calculus classes. So that we're not going to do because I can't. But here's what I do, even though you hate it. You don't get 3 exams or 4 exams in a university calculus class. You get 1 midterm, sometimes 2. So some of you wanted on your thing, you wanted more tests. I am giving you quizzes, okay? And that sometimes you get, usually once a week, not 3 times a week. But you like the quizzes. But in terms of exams are, these comprehensive exams. And that's how it is at the university. And it's important to get used to that. Okay, you're not going to have many exams. You're going to have 1 or 2 midterms, 1 midterm or 2 regular exams, and then a final. So that's typical, just let you know. The whole online thing, that I don't have any choice on. I wish I wasn't doing that, but we have no choice in that. So sorry about that. Some of you don't like the online thing. I can't. It's not in my power. If I had the power to get rid of COVID, I would go like that. It would be gone. But I have no power. So sorry about that. So we have to be online. I can't do anything about that. I'm just addressing some of the things that you talked about on the extra credit. So I can't give you more than that many exams. I'm not going to drop an exam because that's not done when you have your 1 midterm or 2 regular exams. Sometimes they'll drop a homework assignment, but that's so unimportant anyway in terms of the numbers. But in terms of university, that's kind of how it really is. Just let you know that. So sorry about that if you hate it, but that's what you're going to get when you get to university. I need to get you prepared. I'm treating this as, a pretty upper level class. You're at the top of your college, basically, or close to it. Next year, it'll be totally top if you take the second year calc. So that's just a note about that. One thing that everyone in the entire class got wrong, it's depressing for me, was the last problem, the last true false. Do you remember that one?
Those are true and false.
The last true false, the second true false. There were 2 true falses.
Oh, everyone put the wrong true or false. Like if it was false, we put true, and if it was true, we put false.
Yeah, I mean, everyone got the same question, but that was when if you have two spherical coordinate functions, and such that if you set them equal to each other, you get no solution. That does not mean that they don't intersect. And that's a big issue with both polar and spherical, actually. I could have used the word polar instead of spherical. It wouldn't have made any difference. It's a big issue because what the issue is that if you move by 2 pi for either theta or phi, it doesn't matter. What happens? What happens to the point if you move it 2 pi, either theta or phi?
It goes through a whole cycle.
Yeah, it doesn't change. Does that make sense? It doesn't change. So it's a big issue with spherical coordinates and polar. It doesn't really make a difference. And I want to mention that because everyone got that wrong, and it is an important thing, is that you can't just set the equations equal to each other and think you have them all, because you have to deal with this horrible fact that if you add 2 pi to the angle, you don't change the angle. So even though if you set the 2 equations equal to each other and you get no solution, it might be because the angle's been adjusted by 2 pi. Does that make sense? And it's a big problem with polar coordinates and spherical coordinates. And in fact, with spherical in phi, I don't think I've mentioned it enough, but do you know what the period is for phi? Or how high you need to go? Okay, it turns out it's just pi, it's not 2 pi. And if you think about it, because if you start at the top of the z-axis, positive z-axis, and you go pi, then you're down at the bottom. And bottom to top is everything. Okay, so in that case, even if you add pi, you could have all kinds of problems. Okay, or you add, a little less than pi and a little more than pi, let's put it that way. So I just wanted to mention that because nobody got it right. I didn't mean it to be a trick question. It's something I mentioned in class, but that doesn't mean you remember everything I say. That's a big problem with polar and with polar coordinates or cylindrical coordinates and spherical coordinates, is that you get this overlapping issue. Any questions on that? Because it was a big problem for you guys. Okay. I just want to kind of mention, I want to mention the things where just a lot of you made mistakes. That was the biggie. Was that true false just killed y'all? And I did not, I never know what's going to zap you. That was not meant to be a zap you question, but it turned out to be. Okay. So it's kind of hard for me to get that down. But that was the biggie. Let's see. I mean, the other true false, some of you got the other true false right, but not all of you. The other true false was if you have tangent lines to a surface that are parallel, well, remember the gradient is always perpendicular to the tangent line. Well, if you have two that are perpendicular to something parallel, then they must be parallel itself. That's all that is. So that came up. So I just want to mention a couple things that I noticed that the true falses are, and again, that's typically true falses are hard for people. I didn't expect 100% to get it wrong, the last one wrong, but just a note. Any questions? Any questions about the exam? Any particulars? Hopefully you all got my comments. I try to put in like pretty detailed comments. Okay. And by the way, if I skip a number, do you know what that means on the comments? Yeah, it's a congratulations. Okay. I only have so much time, so I can't like write stuff for every single problem if you get it right. So, so if I skipped a number, that does not mean I forgot. It just means you got 100% on it. And if you get 100%, that just says great, good job. Okay. Any questions on that? So I figure I should mention about my grading, the way I grade. But you should be able to look at my comments. Are you able, because I can't tell because I don't take the test. Are you able to see the test now? So when you open it, does it open for you? You can look at it and see what you got wrong and stuff. Okay. Okay, good. Again, it's hard. I'm the instructor, so I can't see. I have a student view, but only a student view if I took the test, which I didn't. So good. So I'm glad you can see it. So what you should do, not necessarily today, when should you do this? When should you go back and look at the whole test, look at my comments, and make sure you understand everything? Yeah. I give it a week before the final. Not the hour before the final, but like a week before the final. That's when you want to start, reviewing. You have to review a lot because we're not touching this stuff again until the final. So what I recommend is going back and looking at what you've done, look at my notes, make sure you can do everything. Okay. The final, of course, will not cover everything here because the final's slightly longer than the regular exam, and it covers everything we're about to do also. So, it'll be fewer problems, but basically this is content. The other thing to note, and I don't know if you noticed, but the way I write this is I just go back to your quizzes and adjust a little bit. It may not feel like it, but that's what I did. Okay, so the quizzes are your best study guide. Any questions at all on the exam? Any questions? Okay, if there are no questions, then I'm going to go back and literally we're going to put all this behind us. Okay, because we're talking, in fact, before pre-COVID, actually, I did I did it in reverse because it doesn't matter which order we do this in terms of whether we go to whether we do the functions of several variables first or we do sequences series first. So just let you know that you don't need to know anything from the last 6 weeks to do anything we're doing today. Okay. And in fact, to do anything we're doing for the entire rest of the next 5 weeks. Okay, so that's a big note. And in fact, this is going to sound really weird, but once in a while, but very rarely, do you have to know how to take a derivative for the next couple weeks. Okay, well, it's a whole different branch of calculus that we're about to go into. And it is a very important branch. It's going to be a little frustrating for you because the main applications are the last part of this stuff. So basically, it's going to be maybe 2 or 3 weeks before we even talk about any main applications. Okay, so that's just a note, which is why I want to talk about the application presentations right now, because for the next 3 weeks, we're not doing many applications. So your applications will probably come from the stuff we have on the exam. So let me go back to the syllabus. And let me read it up a little bit. So first thing, the presentation is due June 4th, or is on June 4th. Okay, so presentations are on June 4th. So that's important. You need to be logged in on June 4th. That's a day that you have to be here. Okay. So whatever you've got going on, you need to be online that day. And then over here, I think I talk about it somewhere. Here they are. Okay, so let me remind you from the first day of class, because we kind of talked about it a little bit, but now we're going to read every word of it and talk about them. Is the application presentation involves investigating an application of calculus, and in particular, the stuff we've been doing. So the first half of the class. If you can find the sequence and series application, that's great too, but they're harder to find because we won't see applications for a few weeks. Okay, you must present with at least one and no more than 2 partners. So in other words, you have a pair or a trio. Okay, so what you can do now, like as I'm talking, you can put in the chat box looking for a partner and see if you can partner up right now. Might as well do it. That's easy. So while I'm talking, you can see if you can find partners and get that presentation, so that you know who you're going to work with. Okay. You'll be presented on June 4th. You're going to give a 5-minute presentation to the class, and you're going to be using online technology. Okay. So online technology obviously means Zoom, but you're going to share your desktop. Okay. And you could either have one person do all the sharing, or you can go back and forth. That's your choice. But you want to practice it. And I'm going to grade it on both content and presentation. So one thing obviously needs to have calculus in it. So, and that could be dot products and stuff like that too, but it needs to have what we've done in the class. And you also need to present as a group. So if there's 3 of you, I need to hear all of you talk. Does that make sense? Okay, so you take turns. You all have your mics on and you take turns talking. And let you know, I'm going to let you choose whether you want it recorded or not. Okay, or put it on YouTube. Okay, I mean, I could record it, but if I record it and throw it out, who cares? But I'm going to let you choose whether you put it on YouTube. I'm going to ask you on that day saying, are you comfortable with having this up? And if you are, then it'll get put up. If not, then what I'll do probably is I'll go back and I'll edit out your piece so that it's not on YouTube. I think that's the easiest for me technologically to do. So that's what you're going to be doing. So you could do like PowerPoint or whatever your favorite PowerPoint-like type thing is, so that you have it all ready. Any questions about the application presentation? Any questions? Okay, I know you have, you have a few weeks for this, like 2.5 weeks, something like that. And I'm happy to answer questions anytime. I have office hours, whatever. When I ask you questions at the beginning, that's a good time too. But anytime you have questions, just let me know and I'll answer questions. But you must have a partner. It's not optional. Okay. And why is 3 people better than 2 in a group? Any ideas? Yeah, less work per person, right? So if there's 2 of you in a group, you each have to talk 2.5 minutes. If there's 3, you each talk, 1 1/3 minute. Okay. And I don't know, it's easier to talk less, and also prepping too. Okay, there's less prep because you can split up the work. Because you want to prep, you want to make this this is not one on the fly kind of stuff. You need to work ahead of time on this one. And I'm here to help you. Okay, and so are the tutors, by the way. Okay, any questions before I move on to the second part of this course? Okay, so let me move on to the second part of the course. And that is the definition of a sequence. Now, you've all seen the word sequence before. Anyone know what it is? Anyone tell me what a sequence is? Okay, it's a pattern. Actually, the funny thing is it doesn't even have to have a pattern. Okay, for example, if you listed, I don't know, the temperature today, the temperature tomorrow, the temperature the next day, and you do that for years and years, you're not going to see much of a pattern. Okay, especially if you do it in, say, Point Reyes. I don't know if you know about Point Reyes, but that's where they're like no seasons in Point Reyes. It's always cold, miserable weather. But it doesn't get freezing, doesn't get warm, but it's all, it changes here and there. So it actually doesn't even have to have a pattern. But most of the sequences we're going to deal with have patterns. You know what a sequence is? Because you've all seen it. You've all heard the word. I can't imagine you not having heard the word sequence. Okay, an ordered list of values. Okay, that's a good way of saying it. That's a good way of saying it. So it's an ordered list of values. I'm going to show you the better definition. Okay, ordered list of values is just fine. But I'm going to use a definition that uses the most important word in all of mathematics. Anyone know what that is? I think I've mentioned this before. Of all mathematical terms, vocabulary words, function. Yeah. So a sequence is going to be a function. But we got to think about what's the domain. When you have a function, you have a domain and you have a range. What's the domain of the function for a sequence? And you have to think for a while because you probably never thought of it this way because you haven't had to think of it like write down a formal definition using mathematical language, but we can. Okay, and of course, what's the range of a function? So let me pop up the big definition. And that is the following. A sequence is a function with whole numbers or natural numbers, actually. That really depends on, I don't know, what field you're in. Whether you want to use whole numbers or natural numbers typically as your domain. Okay, as a domain, and real numbers as a range. Okay, and in this class, sometimes we'll use whole numbers, sometimes we'll use natural numbers. Let me ask you, just in case you don't know, again, this is something you get in beginning algebra. Do you remember what the differences between whole numbers and natural numbers are? It's very simple. Doesn't mean you know it or remember it. Remember what those vocabulary word means? What's a whole number? What's a natural number? What's the difference? Okay, natural numbers, sometimes they call the counting numbers. When you count, where do you start? You all know this. You learned this when you were like maybe 2 years old. Where do you start when you count? Because it's going to be important for what we're doing in this chapter. Yeah, you start at 1, 1, 2, 3, 4, 5, etc. Okay, you learn that when you're, like I said, 2 years old, maybe 3, depending on what your parents were like. You start at 1. Okay. On the other hand, any computer programmers in our group? Do you have anyone that does any programming, like myself? If not, I recommend learning it because it's a very valuable thing to know. Any language, I don't care. They all use the same counting system. Okay. So in computer programming, you don't start at 1. You start at 0. Okay. And that's standard. So you can trust me. I know probably 10 different computer programming languages. They all start at 0. Okay. It's just the standard thing. Okay. And you have a sequence. It starts at 0. So for computer programming, you start at 0. And for more of like day-to-day stuff, you start at 1. For mathematics, you start wherever you feel like it, whatever seems to work best for you. Sometimes you start at 0, sometimes you start at 1. Okay. Occasionally you'll start at 2 if 1's not defined, but usually 0 or 1. Just let you know that. For our main application, which is called Power Series, we're going to start at 0. Okay. It will be standard. Okay. Any questions on a sequence? What a sequence is? Okay, we're going to be dealing with them and working with them a lot for the rest of the class. Let me give you a fun example. Word worked better a month and 3 days ago. You don't know why? I know you weren't even in my class. Oh yeah, you were in my class. Yeah, class had already been gone. Yeah, so here's the sequence. Okay, it's one of my favorite sequences. 3, 1, 4, 5, 9, 2, 6. I'm hoping you all recognize this sequence. All right, this is a sequence of digits of pi. Okay. Is there a formula for it? Okay, and this is a tough question. I didn't expect any of you to know. The answer is yes, but it's but we won't. We'll actually get to the formula, or there's more than one actually. We'll get to a formula for it in about 3 weeks. Okay, maybe 4. So we'll talk about the formula that gives you this sequence. Okay, and it doesn't look anything like pi. Doesn't have sines or cosines or anything like that. It's really cool. So we'll talk about this kind of sequence. Okay, so this is an example of a sequence, and that's what sequences are. You usually write them. There's a few ways of you can write them. One way of writing is a list of numbers. Okay, and that's okay, but the problem is that it can be misleading because the problem is ... Well, hopefully that's pi, but I don't know. Maybe it's pi plus 0.00000006 or something. So that's the only problem with writing it as a list of numbers with ... is that sometimes it's misleading. Okay. For example, if I said 2, 4, 6, you might think the next number is an 8, right? But there's other interesting functions that actually start with 2, 4, 6, even though the next number is not an 8. Okay, so just a note, it's a little dangerous to write it this way. So instead of writing it this way, there are 2 standard ways of writing it. And let me give you those definitions. So the first is a sequence is given explicitly if it is written as A sub n equals f of n. So you can write down what the sequence looks like as a function So you really get down to that definition where a sequence is a function with domain whole numbers or natural numbers and range real numbers. So a couple notes. One, I purposely did not write f of x. How come? Why did I not write f of x right here? Any thoughts?
Because it's a to n, not a to x.
A to n, not a to x. Right, but I could have written a sub x equals f of x. Why did I use n? There's a reason. Very important reason. And we're going to be using it all the time.
Does it stand for number?
Yeah, but a special kind of number, not just number.
Natural number?
Yeah, natural number. N for natural. So really N for natural. Okay. It can be whole too, by the way. You don't want to use X because when you use X, that almost always means X is a real number. But here, X is not a real number. It's a whole number or a natural number. Okay. So in other words, this f of n, it'll never be f of 3.21 because 3.21 is not part of the domain. Okay, instead, n is a natural number or possibly whole number, and that's why we're going to be using n. We typically write it as a sub n. So again, whenever we're doing something new, like very new, and this is day one of the rest of the entire class in terms of the topic, it's very important to get down the notation. And the notation we use to talk about a sequence is a sub n, is your standard sequence. Okay, and if there's two of them, I bet you can all guess. If a sub n would be the first one you write down, and then you want another one you can compare with, what do you think you're going to have that in general be? It's not a trick question.
A sub n2.
No, good try. Just like if you have f of x as your standard function.
A sub n minus 1.
No, let me go here. If f of x is your standard function, and you have another function, it wouldn't be f of x1. It would be g of x, right? Would be another function. So if a sub n is your standard first function, what do you think the standard next function might be?
B sub n?
Yeah, b sub n. What do you think the third one would be?
C sub n?
Exactly. Okay, and not only that, you can even get a fourth one, d sub n, because as I mentioned, we're not really doing derivatives in this class anymore. So you can get along with d now. D is now fair game for using it as a variable. Okay, I know it's hard to get used to in calculus, but we're leaving derivatives for a while. Okay, so for this chapter, d is fair game. So we're going to have, A, B, C, and that's how we're going to be listing or writing down different sequences. So again, notation is very important, and we use and I don't get mad at me because I'm not the one that did this, but for some reason we don't write a parenthesis n paren. Everyone in the world uses a subscript n to talk about sequence, and it's just the way it's done. So it's not me being picky, it's me telling you how everyone in the world does it. Okay, so a sub n is the way you write a sequence. Okay, and if you can write it as a function of n, then we call it explicitly shown. On the other hand, you can have it recursively displayed. Okay, and it's recursively displayed if the first term or terms are given, along with how to calculate each succeeding term from the previous term or terms. And that's called recursive sequencing. And if any of you had any computer programming past, Have you heard of recursive functions in computers? Yeah, that it happens in a big way. Okay. What is the problem in computer programming and also back in math too with recursively defined functions? Anyone know in computer programming? There's a big problem with them. And it's the same problem in regular writing, but those who computer program, you totally understand it, hopefully. Okay, it has to do with RAM. You know what RAM is? It has to do with RAM. So in order to get, if you have a recursively defined function and you want a sub 1,000, well, to get a sub 1,000, you need to pop it in from you start at a sub 1, and then you go to a sub 2, then you go to a sub 3, then go to a sub 4, and you keep going until you get to a sub 1,000. And that takes a very long time. And if there's branching, it's actually 2 to 1,000 different computations, which is more than a computer can handle, and you crash your computer. Or even worse, you crash your brain if you try and do it by hand. Y'all agree? So recursively defined functions are dangerous, but sometimes that's the way you have to do it because that's all we've got. Explicitly is better if you can do it. So let me give you some examples. Okay, so the first one, a sub n equals n squared over n plus 3. If I asked you what was a sub 100, could you tell me? How long would it take you to tell me, at least? Yeah, a few seconds, okay? Right, 100 squared, you may not know. Yeah. You could plug in your calculator, or I plug it into my calculator brain. 100 squared is 10,000, 10,000 over 103, I'm done. Yeah, I could use a calculator, but that was faster. Okay, do you see how fast that is? Okay, now let me give you another example. And that is a sub 1 is 1. A sub 2 is also 1. Sounds good so far. And a sub n is a sub n minus 2 plus a sub n minus 1. Okay, if I asked you what is a sub 100, could you tell me? Could you do it in a few seconds? Yeah, probably not. Okay, now definitely not. And even computers might have some issues with something like this. Okay, but it still can be done, right? Because you say, well, we know a sub 1, we know a sub 2, a sub 3 is a sub 1 plus a sub 2, which is 2. 1 plus 1 is 2. A sub 4 will be a sub 2 plus a sub 3, or 1 plus 2 is 3. A sub 5 would be 2 plus 3, which is 5. And I could do this until I got to 100. Okay. But that is torturous. Do you agree? Okay. Even to a computer, computers will start spinning on you. Okay. Well, a sub 100 will probably be able to handle. A sub 1,000, maybe not. All right. So one thing is, have you seen this sequence before? The answer is probably yes. Doesn't mean you recognize it as a formulas, but it has a name. Anyone seen this sequence? Right, it's 1, 1, 2, 3, 5, 8, 13, 21, 34, etc., etc. Anyone seen this? It's very old. Okay, it's called the Fibonacci sequence. you heard of it? It's called the Fibonacci sequence. And it's actually used in biology. That's how it was originally introduced as rabbits, because they like to multiply. So that's a typical recursive sequence. Okay. By the way, do you think this recursive sequence can be written explicitly? Do you think it can? Do you think there's a function like I have, like it's not n squared over n plus 3, but do you think there is a function that you can write? Okay, so the answer is yes. But the follow-up on the answer is that we can't understand how you get it or what it is until we get to linear algebra. And that's winter quarter of next year. So just a note is that we're not ready for it. It's pretty advanced. Okay, and it can be done, but you need matrix theory, which I'm not going to do. But I wanted to let you know that there's lots of different kinds of sequences. Okay, and sequences are important. Are there sequences? Can you think of a sequence that occurs in the real world other than rabbits multiplying like the Fibonacci? Where do these sequences happen? And there are lots of places. Driving speed limits? Maybe need more explanation because I am not sure why that's a sequence.
Sequence of like when does it go faster and when to go slower. Like you merge onto a residential street and it's like normally like 25, but if you merge on freeway, it's like 65.
Yeah, I'm not sure if that's a sequence though, because that would be remember, it'd be a list of, it's a function, right? So what
it's
would
not
f
linear.
What would f of 3000 be? Or a sub 3000 be? Yeah, I don't think so. Nautilus shells happen. And Nautilus shells, I'm not going to get into it too deeply. Believe it or not, involve the Fibonacci sequence. That is the sequence. It's an adjusted Fibonacci sequence, but that happens. Let me give you some others that you all know about. And that is loans. Okay. Hopefully you don't have two bad ones. But let's say you have a student loan. You graduate from college, and let's say you owe $40,000. Okay, it's scary, but that's typical. And most students can't pay the $40,000 the day after they graduate from college. It's not what you do on graduation day. Then what do? Then every month you pay some money, right? Yeah. You pay money, and you might be able to afford $500 payment. So every month you pay $500, but that $40,000 accrues interest while you're paying money. So each month you can look to see how much you now owe, hopefully less than what you started with. And you can talk about what is that sequence. Okay, any questions on that? So that's an example of a sequence that happens. Okay, let me give you another example of a sequence that happens. In the course I'm doing now, not teaching now, by the way. I don't know if I've mentioned, but I start every morning off. Unlike you guys, you probably wake up and do this class. I wake up at 5 in the morning. I've already watched a whole lecture, and the class I'm watching is genetics. And sequences are really important in genetics because if you have a mother and a father, and the father has a genetic mutation, and you want to look under the progeny, generation to generation to generation, then what is the probability that each of the next generation, next generation, next generation will have that genetic issue? And that is a sequence, and it goes forever. Okay, even though eventually we'll probably all die out, but you can at least in theory do it forever. Okay, and by the way, you can do forwards and backwards. So nowadays, okay, this didn't happen when I first started teaching, by the way. Nowadays, any of you can go and get your your saliva grabbed, and they can look at your DNA. And then you can find out everything, I don't know, but everything about yourself, but you can find out a lot about yourself. Do you know how that's done? Sequencing. So what they can do is they can look up generation by generation based on what your DNA is. And from reverse sequencing, they can talk about where you came from. Isn't that kind of cool? Okay, and all that is done using this sequence stuff. Okay, and it's not a continuous function because there was no genetics halfway between your mother and you, right? You instantly happened. Okay, I'm not going to get into the sex and all that, but hopefully you understand that. You instantly happened, the sperm hit the egg, and you instantly occurred, basically. So that is truly a sequence where we're not talking the domain being real numbers, we're talking about the domain being whole numbers or natural numbers, whether you consider yourself as 0 or 1, that's your choice, in terms of the starting point. And then you can go up the generations. And then when you go up the generations, then you end up with these sequential patterns in genetics, and then you can actually do all kinds of cool stuff with it. Any questions on that idea? Any questions? Okay, and then in math, we're going to learn that things like sine of x can be written as a sequence. Okay, it doesn't feel like it. It just looks like a function. But it turns out it can be written as a sequence. But that's not today. Any questions on the idea of these sequences? Okay, so now comes a big deal. And we're going to be spending a huge part of the rest of the class on this definition. Okay, not memorizing the definition, but deciding whether a sequence converges or diverges. In fact, I forgot to make it red. So a sequence AN converges to a limit L if, and you're used to this in calculus, if for every epsilon greater than 0, there exists a capital N such that the absolute value of A sub n minus L is less than epsilon for every lowercase n greater than capital N. And then otherwise, instead of converges, we say the sequence diverges. So let me make it red because diverges is a very important word. Okay, I'm going to read it again. That's how important this is. So a sequence AN converges to L if for every epsilon greater than 0, there exists a capital N such that the absolute value of A sub n minus L is less than epsilon for every n greater than n. Okay, so I want to mention a few things. When you're talking about whether a sequence converges, do you care about what happens in the first 500 values of the sequence? What do you think? Okay, not too much, actually, not at all. Okay, when we're talking about convergence, we're only looking at way out there, and way means as far as you can imagine, you're not even close. Okay, because basically we're taking a limit as we're going off to infinity, and we're finding out as you go off to infinity, do you tend to go to a number or do you not go to a number? Okay, what happens in the first 100 or 1,000 or whatever numbers is irrelevant. The pattern matters, but not the numbers themselves. What matters is what happens at the end, even though there is no end technically. So that's one big deal. Converges is really important. Let me tell you, in the real world, in the real world, we're talking computers now, and the computer will often be able to take a sequence and give you as many decimal places as you want by saying, well, we'll go off to 10,000 in the function. Does that make sense? And we'll use that one. Why do you care about convergence? Any thoughts? Okay, I'm not seeing y'all jumping in. Okay, so the idea is if you go off to 10,000, you're saying, hey, I've probably gone far enough. I've gone way the hell out there. But if it diverges, that 10,000th number is meaningless because there is no answer. And what's going to happen is computer is going to pick, going to stick out a number. It's going to push out a number and say, this is the answer. And it's completely wrong because it diverged. Computers can't handle infinity. I don't know if you realize that. Okay, computers only have a finite number of stuff it can do. So computers can't handle infinity, so it just gets a huge number, uses that, and say that's got to be good enough. But if it diverges, it isn't. Okay, and that's why it has to be checked to see if it converges or diverges before you pop it into the computer. Any questions on that idea? Okay, so this is a major thing. Is it obvious if a sequence converges or diverges? Just by looking at it? And the answer is it's kind of a trick question. Sometimes. Sometimes it's obvious. Sometimes it's very difficult, and sometimes it's impossible to know. So we're going to see all different cases about convergence and divergence. And we're going to spend most of the rest of this course understanding convergence and divergences. And in fact, we're going to look at special sequences. And those are series, and we'll understand why series are sequences. Okay, any questions before I move away from this main definition? Before I do examples. Okay, or actually do a couple theorems before I do the examples. Okay, I could do one example that hopefully I'm going to do some obvious examples. Let's suppose that A sub n equals 7. So that means the sequence is 7, 7, 7, 7, 7. Hopefully you're getting bored. Does this sequence converge or does it diverge? Yeah, this one converges. It converges to 7 because it's just always 7. So in this case, for every epsilon greater than 0, pick any n, it doesn't matter because after that, you're always at 7. 7 minus 7 is 0, and that's always less than epsilon. There's nothing to it. Okay. How about, I'm doing easy ones, and then we'll get to harder ones, and we have some theorems. A sub n equals n. Converges or diverges? So by the way, that's 1, 2, 3, 4, 5. I hope you know how to count. Does that converge or diverge? So let me write 7 converges. Yeah, that one diverges because if it converged, it mean it would converge to a number. So if you gave me a number, then I just say, well, let n be a little bigger than that number, and guess what? You're not going to be within even 1. Does that make sense? So that one diverges. Okay, so I wanted to give you some easy examples first, and then we'll start learning how to do harder ones. Okay, and then I'll show you the most important of all examples, a whole group of them. So here comes a theorem. And it's an important one. We'll use this one a lot. And that is let an be a sequence and let f of x be a function such that f of n equals a sub n. Then if the limit as x goes to infinity of f of x equals L, then the limit as n goes to infinity of a sub n equals L. Okay. So let me give you an example. Let's suppose a sub n. And I'm not going to prove this. It involves epsilon delta stuff. And I don't want to spend the whole time on epsilon delta because then we'd have no examples. So if you want to learn about this stuff, take real analysis in a couple of years at your university. It's beyond community college. So let's let a sub n equal 1, how about 2 plus 3 over n. Let me get it. Okay, again, epsilon delta is not, you don't want to do that because that's no fun, because it can be done with epsilon delta. But instead, this is easy. Can you think of a function of x such that f of x, f of n equals a sub n? The hint is it's very easy. Okay, anyone tell me a function of x such that f of x equal f of n equals a sub n? Hint is it's obvious. Yeah, 2 plus 3 over x. And clearly, f of n equals 2 plus 3 over n. Okay, now hopefully you remembered your very, very basic calculus. And what is the limit? Of as x goes to infinity of f of x. It's 2. Okay, because 3 over infinity goes to 0. 2 plus 0 is 2. Okay. So because of that, by the theorem, we can use the theorem, and we can say the limit as n goes to infinity of a sub n must be equal to 2. And I just found it. Any questions? Any questions on this idea? Okay. Do you think this is going to work for every sequence we ever deal with? Do you think this is the way we're always going to find the limit? Yeah, the answer is definitely not. And the big reason why it's definitely not is finding that f of x is very hard sometimes. Okay, trying to come up with what is that f of x is harder than you can imagine for many very important examples. But for the simple ones, it works and it's easy. Any questions on that? I also want to let you know that this is a one-directional theorem. Okay, this says if the limit is L, so in other words, if it converges, then an must converge also. So in other words, if f has a limit, then an converges. It does not mean that if f doesn't have a limit, an doesn't have a limit. Okay, you can't go backwards. Any questions on that idea? Okay, and let me give you an example of why you can't go backwards. Going to give you a really easy example. A sub n is equal to 0. Okay, does that converge or does that diverge? If it's the sequence 0, 0, 0, 0, etc. Converge or diverge?
Converge or?
Yeah, converges. Converges to 0 because it's always 0. Constants are easy. On the other hand, let's look at f of x equals the sine of pi there's pi x. Okay. Are you convinced that f of n is a sub n? That the sine of pi times n is 0, no matter what n is? Okay, I hope you know that, right? The sine of n pi is just 0. On the other hand, if you take the limit as x goes to infinity of f of x, well, the sine of pi x, now we're talking about x. We're not talking about integers anymore. Now x is a real number. Sine, hopefully you know, goes up and down and up and down and up and down forever, right? This doesn't have a limit. So you got to be very careful. You cannot say, I found a function that where the limit didn't exist, therefore the sequence diverges. You can't say that. Okay, it's a one-way theorem. Any questions on that? So it's important to, see this example. I tried to pick one that hopefully you all can see. Coming up with it's hard if you're not, used to this stuff. But hopefully seeing it makes some sense that this particular a sub n clearly converges, but f of x, which does match a sub n for integers, that doesn't have a limit. So it's a one-way theorem. Any questions on that before I move to the next? Okay, we have a lot of information today because there's no quiz to deal with and not a lot of questions either. All right, so here's an example. Let's see if you can do it. I want you to try. Prove that a sub n equals 2n plus 3 over 5n plus 7 converges. So see if you can prove that this is a convergent sequence. And I'll give you a minute to try and do that. Okay, and the hint is use the theorem, don't use epsilon delta. Yeah, it's going to converge to 2/5, but that's not a proof. That's a what it converges to, but you haven't proven it. And it's not that hard, but it's more than just saying 2/5. Okay, and I will let you know that kind of an easy way to do it involves someone French. That's a hint. So let's see if you can give this proof. And don't do it the hard way. Don't do it with epsilon n stuff. Do it with a theorem. So give you another minute. Shouldn't take too long. All right, proof. Okay, Rigney, you're pretty good, but you should write down what f of x is. So let f of x equal. So we need to actually say what is f of x. And in this case, f of x is equal to 2x plus 3 over 5x plus 7. Okay, then clearly f of n is equal to a sub n, because we're just substituting n in where we see an x, and that gives you a sub n. But then by L'Hopital's rule, and let's see if I can do it this way. The limit as x goes to infinity of 2x plus 3 over 5x plus 7. Notice you get infinity over infinity. That means we can use L'Hopital's rule. Is equal to the limit as x goes to infinity. And now I can take the derivative of the top and the bottom. And that's 2 over 5. But that is 2/5. There's no x's, and it's just the number. Therefore, by the theorem, a sub n converges. Any questions on this proof? Any questions? Okay, let's move on. Okay, we have what's called, the book calls them the algebraic limit laws, but the number 6, they don't use number 6. They talk about that right after, but I'm just going to call them the limit laws. They're all pretty obvious. So I'm going to go through them really fast. I think you'll agree they're obvious. And that is if we have the limit as n goes to infinity of a sub n equals a, and the limit as n goes to infinity of b sub n equals b, then the first thing is the limit as n goes to infinity of c equals c. Nothing to do with the a and b, by the way. That's obvious. If you just have a constant over and over and over again, and you go off and you say what's going to be like, an infinite number of steps, it's still going to be the constant. That's all that is. Okay, number 2 says the limit as n goes to infinity of c times a sub n is c times the limit as n goes to infinity of a sub n is ca. So that just says that you can pull out a constant, kind of like integration or derivatives. You can pull out a constant. Very important. Number 3 says that if you take a limit as n goes to infinity and you're adding two sequences, an plus bn, or you're subtracting, you can split them up. And you could say it's the limit of an plus the limit of bn, or minus the limit of bn. And that's going to be a plus b or a minus b. Any questions on that? Okay, the next one says same is true with multiplication. So the limit as n goes to infinity of a and bn is ab. And the next one is same is true with division, and you're used to this, you can't divide by 0. So the limit as n goes to infinity of an over bn is just a over b as long as you're not dividing by 0. Dividing by 0 is always bad, right? And then the final one is the limit as n goes to infinity of f of an will just be f of a. You can pull a function out if the function is continuous. Any questions on these limit laws? They basically say you can do what you want to do, which is nice. I don't think I need to do much with it, except we'll be using as examples, and they'll say, oh yeah, you just split the plus or pull out the constant. Okay, it's very similar to integration, except with integration, of course, you don't have products and quotients so nicely. All right, so I'm going to move on and then talk about the next one, which is also should be pretty obvious, especially with the word squeeze. It's called the squeeze theorem. And it says that if Bn is between An and Cn for all large n, and if the limit as n goes to infinity of An is the same as the limit as n goes to infinity of Cn, then so it is for Bn. Okay, and this is called the squeeze theorem because you can say B is kind of getting squeezed from below by A and above by C. So I like to think of it as a sandwich theorem, is that A is the bottom piece of bread and Cn is the top piece of bread and Bn is the stuff in the middle, your sandwich meat or whatever. And the idea is if A and C end up in the same spot and B got stuck between them, whether it's the same spot. Any questions on this idea? We'll use it from time to time, not too often, but once in a while, just when they least expect it, you know that is. Okay, so that's the squeeze theorem. Kind of going through those quickly because it comes up once in a while. Okay, the next is boundedness. And you've seen these words before, but now we can talk about it for sequences. So A sub n is bounded above by m if A sub n is always less than m. So that means that you can draw a line so that all the points stay below that line. Okay, and similarly, if there's a line such that all the points stay above that line, then it's bounded below by n. Okay, and an is called bounded if it's both bounded above and below by two different numbers. Okay, and an is always, if an is always decreasing or always increasing, then we call an monotone. So this is language, those are just words. So we've talked in calculus, you talked about increasing and decreasing functions. So it's actually the same definition. Is that if as a function, if it's increasing, or if it's decreasing, then it's monotone. And we'll often say monotonically decreasing or monotonically increasing. Any questions on this language? Any questions? So just let me throw out some examples we've already looked at. So for example, this guy. Is it bounded? Yeah, this is bounded. Okay. In fact, you can just grab a number like 100. Do you all agree this will never get bigger than 100? Is that clear to everyone? Okay, and hopefully you know that it'll never get smaller than 0. This is never negative, right? For all positive n, you can't get a negative number when you take 2n plus 3 over 5n plus 7. So an is bounded. Okay. How do you decide if it's monotone? If it's monotone? What's the easiest way? And you may not remember it. And it still takes some work, by the way. We're just going to get a strategy. Think if there's powers involved. That's not enough. Okay. So let me tell you how to do it the nice way. If you go over here and you remember how you did in calculus, how did you find out if something was increasing or decreasing? Calculus, that's a hint. Plug in points, that's not how you did in calculus. Yeah, you took a derivative. And if the derivative was positive, then it is increasing. If the derivative is negative, it's decreasing. Okay, and in this one, at least for large n, and that's all that matters, for large n, this turns out if you take a derivative, you'll end up with negative numbers. Okay, and you just trust me on that one, it will work. So that's how you can see, is it decreasing or is it increasing? Typically, you relate its function, okay, if it's messy like this. Take a derivative and see if you get positive or negative. Sometimes it's obvious if it's increasing or decreasing. So for example, how about this one? Is this monotonic? One more guess? Yeah, this one is monotonic, right? As n gets larger, an gets smaller.
Larry, what if you start at 0 and then move to 1? Doesn't that go from 2 to 5? And then as you
okay, first thing this implies,
okay,
first thing this implies you don't start at 0. And we're only looking for big numbers. Big numbers is all we care about, by the way. But okay. 0 doesn't even work. Can't even plug in 0. Does that make sense? So if I plug in 1, I get 5. If I plug in 2, I get 3.5. If I plug in 3, I get 3. It's going down. Do you see that?
Yeah, I kind of forgot about dividing by 0 doesn't work.
Yeah, you don't even go to the 0 thing. This one kind of implicitly, this is saying n it starts at 1. Otherwise, you wouldn't even write it down. Okay, but I want to kind of mention what the language is, and that's the language. Okay, let me continue on. Okay, so if AN is a convergent sequence, then AN is bounded. Okay, and I want to let you know that doesn't mean that if AN is bounded, then AN is convergent. This is not how you decide. This is not how you prove a sequence is convergent. This is how you prove a sequence is divergent. Okay, because it's really the converse of this, or the contrapositive, I should say, the contrapositive of this statement that is what we're going to use. And that is that if AN is not bounded, AN is divergent. That's a little bit of logic. So an example, let's look at n squared plus 1 over n plus 2. Does that converge? Okay, and you look at this, and you realize this is not bounded, right? As n gets large, this gets larger and larger. Do you see that? Okay, and it's linear large. Okay, so it doesn't peter off or anything. So since this is not bounded, it diverges. Any questions on the example? So the theorem can be misleading because it looks like you use it to show convergence, but you actually use it to show divergence. Okay, any questions on that? Again, a lot of details today. And now we're moving on to the next section, and I'll let you know we're going to spend the entire rest of the course on infinite series. That's all we're going to do from now on. So the sequence was important to be able to understand series, but really this class, the rest of the class is all about series. This you got a little bit in second quarter calc, first week. And that is an infinite series is the limit as k goes to infinity of n equals 1 to k of a sub n. And usually you don't even bother with the whole limit notation. It's too much work. You just write n equals 1 to infinity of a sub n. That's kind of notation. Okay. And then the partial sums are saying instead of going to infinity, just go to k. So summation n equals 1 to k of a sub n. And I will let you know, it doesn't have to start at 1. I just kind of used 1. Otherwise, I think it gets too confusing. You can start at 100 if you felt like it. All that really matters is you going off to infinity. So it's an infinite series. So the partial sums are each of these specific sums. If S sub k converges, we say the series converges. Notice S sub k is a sequence. S sub k is a sequence. So let me get, otherwise the series diverges. So let me tell you why this is a sequence. Okay, let's suppose we had the summation n equals 1 to infinity of 1 over n squared. Then what's S sub 1? What's S sub 1? That's easy. That's a hint. What's the summation n equals 1 to 1 of 1 over n squared? Yeah, that's just 1. And then S sub 2 gets a little messier, not too bad though. That's going to be 1 over 1 squared plus 1 over 2 squared, which is 1 plus a fourth, or 1.25. And then there's S sub 3. And that's going to be 1 plus a fourth plus a ninth. Scroll, sorry. So 1 plus a fourth plus a ninth. I'm just going to write as 1 plus a fourth plus a ninth. Okay, and that's some messy number. That's 49 over 36, I think. Just some ugly fraction. Do you think I could do this and do S sub 4 and S sub 5 and S sub 6? Do you think I can keep doing this? Yeah. Do you see I get a sequence? Okay. Now here comes the evil question. Does this converge? Okay, it's actually not a geometric sequence. We'll get that in a little bit. But do you think this converges? Any guesses? Hey, you got a 50-50 chance, right? Okay, the answer does. Okay, and what does it converge to? And I know you're all thinking this, but I'll just tell you anyway, because you all know what it converges to. Pi squared over 6, of course, right? So today we're not going to explain why it's pi squared over 6, but I'll let you know it converges to pi squared over 6, and we'll learn why. Okay, not today though. Okay, but we can talk about convergence or divergence of this sequence of partial sums, and what it converges to is the series. Okay, now comes a biggie. This is the harmonic series. And it's a series from n equals 1 to infinity of 1 over n. It's just an example. Do you see that? And usually I say example instead of definition. But this is so important. It's not just an example, it's a definition. It is a majorly important series. And the theorem is a harmonic series diverges. Okay, that is not obvious at all. Okay, because we're talking about 1 plus 1 over n, plus, 1 plus a half plus a third. And if you notice, as n gets really big, we're not adding much, right? If n is 100, we're only adding 1 over 100. That's like doesn't add much, does it? So it doesn't even feel like this should diverge, does it? But this diverges. Okay, the harmonic series diverges. And we'll prove this, I believe, on Wednesday. If not, it's Wednesday. It'll be Friday. I'm trying to remember which day we do it. So for now, you need to trust that this series diverges. Okay, and it's not obvious even of 1 bit if you were looking at these numbers, and it diverges very slowly. Okay, diverges, it's going to go off to infinity, but you may have to go to 1 billion before you even got a number like 10. Okay, not 1 billion, but a big, huge, giant number before you even get to 10, and it still diverges. So just let you know that. Okay, now comes the next theorem, but the next theorem is no big deal. I'm not going to spend much time on it at all. And that is basically you could do arithmetic. If the summation of an and bn converge, then the summation of an plus bn is equal to the summation of an plus the summation of bn. What's the last n there? And similarly, if you subtract, then the summation of an minus bn is the summation of an minus the summation of bn. Just means that you can split pluses and minuses. Only when it converges. Okay, all kinds of problems can happen when that diverge. Okay, and similarly, you can pull a constant out. So let me remind you, warning. Without converge, this cannot be used. And I can do a very obvious example. Let me do a subtraction one. And that is, let's suppose an is just the constant 1, and bn is also the constant 1. I'm going to put equals question mark. And I hope you can all answer the question. Is this a true equality? What's the answer to the question? Okay, the answer is absolutely not. I'm hearing yeses. Okay, let's look at the left-hand side. Well, that's a summation of 0. 0, what is 0 plus 0 plus 0 plus 0 going all day long? What do you get? 0. Let's look at the right-hand side. What's the summation of 1? 1 plus, what's 1 plus 1 plus 1 plus 1 all day long? All universe long. Yeah, infinity. Infinity minus infinity is undefined. You can't even go there. So the right-hand side is divergent. The left-hand side is 0. Do you see the problem? So this is false. I'm going to write no. No to the answer to the question. Any questions on that? Okay, now comes a big definition theorem. We're going to be using this a lot today. There's a lot of details today. And that is the summation. And you've seen this before in pre-calc, but now we're going to spend a lot of time using it. And that is summation from n equals 1 to infinity of an r to the n minus 1. Okay, by the way, which is also equal to the summation n equals 0 to infinity of a r to the n, is called a geometric series. And we have the following. If r is less than 1, then the summation n equals 0 to infinity of a r to the n is a over 1 minus r. So it converges. If r is greater than or equal to 1, then the summation n equals 0 to infinity of a r to the n diverges. So this is one of the few examples where you can easily find out what it converges to when it converges. Any questions on the geometric series? I'm going to call it the geometric series test. Any questions? Okay, well, did I? Yeah, I did that. Here's an example. Let's say n goes from 0 to infinity of 4x to the n, where x is some number. What is the solution to this? What is this equal to? So what is the summation n equals 0 to infinity of 4x to the n equal to? Maybe infinity, maybe not. When is it? But it's not always infinity. If it's not infinity, what is it equal to? Using the big formula. It's not a trick question or anything. Look at number 1. That's a hint. You're all saying does not exist, but if x is, say, 0.1, it exists, by the way. Just plug in. A over here, A over there, 4 over here, 4 up on top. We have r over here, 1 minus r on the bottom. So we put 1 minus, and r in this case is x. And this only works for the absolute value of x less than 1. And then for the absolute value of x greater than or equal to 1, this diverges by the GST. And you know what GST is? What does that stand for? This will be our first set of initials. I don't hear you. Geometric series test. So GST is going to be geometric series test. We're going to have a lot of tests, and the abbreviation makes it a lot easier to work with. Any questions on this example? Okay. Typically, by the way, you tend to go from right to left instead of left to right. And we'll get that in a few weeks. Okay, need to move on. We don't have really any time, so I'm just going to go fast. And that is a telescoping series is a series in which most of the terms cancel in each of the partial sums, leaving only some of the first terms and some of the last terms. And often that sum could be just one and no last terms. So let's look at this example. N equals 0 to infinity of 1 plus x squared plus 5x plus 6. And the hint is we can't do this without doing some work. So what did you do in calculus when you had to integrate something like 1 over x? Oh, sorry, there's an error here. That x should be an n. What did you do in calculus when you had to integrate something like 1 over x squared plus 5x plus 6? Do you remember? U sub won't work, actually. You could try it, it won't work. It was a different calculus technique. You may not be writing down what it was because you didn't like it. There is no quotient rule for integration. All right, I'll tell you, even though you don't want to hear it because you probably didn't like it, partial fractions. Do you remember those? They happened, whether you liked them or not, they happened. And it turns out, I don't have time to go through the whole partial fraction things because we're running out of time. If you factor this, you'll get n plus 2 times n plus, oh, you know what? There's a, yeah, that's right. So if you factor this, you'll get n plus 2 times n plus 3. Do you believe that? The simple factoring. Okay, so it turns out if I have 1 over n plus 2 and then go minus 1 over n plus 3, this works. Any questions so far? Okay, this turns out to be a telescoping series, and we'll see why in a second.
Larry, why is it minus?
Partial fractions.
Okay.
If you do it, you get an n plus 3 minus an n plus 2. And then 3 minus 2 is 1, and you get the 1 on the top. This is the, trust me, or you do the partial fractions yourself, and you'll get there.
Oh, okay.
You could write plus -1. Would you rather see it that way?
Yeah, sure.
Okay, but it's the same.
Makes a lot
Hopefully you
easier.
know. Huh? Maybe that
I
makes
was
you
being
happier.
sarcastic.
Does that make you happier? Because then your A and B are 1 and -1.
Yeah, no, it's just I broke the fraction on the, or the equation on the bottom into parts, and I didn't realize that's what you did.
Yeah, and I didn't have time, so I need to get to this. So here's the thing we're going to do now. Now we're going to plug in. So let's plug in, and we get, if n equals 0, we get 1/2 minus 1/3. Then I go plus. Now I'm going to plug in n equals 1, and I get 1/3 minus 1/4. And then I go plus. And then I'm going to plug in n equals 2, and I get 1/4 minus 1/5. Oops. Okay, then I'll plug in the next one, and I'll get 1/5 minus 1/6. What do you notice is happening here? The way I have it in parentheses, it's not obvious, but associativity is allowed. I could write this 1/2, and then I have plus -1/3 plus 1/3. And then I have -1/4 plus 1/4. And then I have -1/5 plus 1/5. Then I have -6 plus 1/6 forever and ever and ever. And all you get, so let me write ... And that's just equal to a half. And that's a telescoping series. So it converges to a half and we're done. So I know it went pretty fast. There are a lot of details today. So hopefully you can follow through these. You can always rewatch it too and read the book. You know, I don't, you know, go word from word what the book is, but I actually go through and I look at all their theorems. I kind of copy their theorems with sometimes nicer language and then come up with different examples, but similar stuff. So I'm going to stop the share because we're a little over time. Sorry about that. And stop the recording.